Okay, this chapter is partially reviewed. What we're actually going to be doing is taking, yeah, dual credit. Thank y'all for working, but can we make sure we're whispering, please? Thank you. What we're going to do is take the stuff we learned in chapter 5 about linear regression and go just a little bit deeper into it and talk about the errors, and what I mean by errors is the residuals. So we're going to talk about the kind of the theory behind the residuals, the assumptions, and then do a little bit of calculation and interpretation. So that's going to be the bulk of chapter 13. In the grand scheme of things, this chapter is anywhere, I think on the AP topic list, it's like anywhere from 2 to 5% of the test. As little as 2%, as much as 5%. So as we're going through this, you're like, oh my gosh, this theory is just making my head hurt. Don't feel bad. I was the same way. If I took a theoretical class in college, I'm just sitting there like, enough with the theory, when can I calculate stuff? So don't feel bad if you feel like that. I totally understand. Let's set the stage by looking at an example. Let's suppose we want to investigate the relationship between your first year of college GPA and your high school GPA. Do you think, oh, wait a minute. What happened? There we go. Do you think you can determine your first year of college GPA just based on your high school GPA? Maybe?
It's just funny people go to like so early you go to college and have like a C. So I guess
so what I mean by this is, can I look at, let's say you have a 3.89 GPA. Can I take that from high school and say, okay, your GPA in college will be this, without a doubt? No, too many other factors, right? So a relationship in which the value of y is completely determined by the value of x is called a deterministic relationship. So if that's getting kind of verbose and you may be thinking, I may not understand this when I'm studying for the AP test, maybe you want to write something like what I just said. That means if x is blank, y will be blank, without a doubt. That's what a deterministic model is. As we said, this is not a realistic model for trying to predict your first year of college GPA. That model is what's called a probabilistic model. That means the description of the relationship between two variables, it can be somewhat determined by your high school GPA in this case, but there's other factors too.
So, like fantasy football? Well, I don't know.
I don't really play fantasy football, but explain it a little bit to me.
Well, it's basically you pick players in the NFL and they be scoring points, but it's like, you know, you never know because it's real life. So, like in the game, they can tell you like, oh, you have this much, and you're gonna win. But like, it always changes. Like, you know, I'm trying to get hurt or something.
Gotcha. Yeah, so kind of like that. So the equation for a additive probabilistic model is your deterministic function plus some random deviation. So we're going to say the deterministic function of x is just f of x. So if we're dealing with a linear model, that would be the alpha plus beta x. That's f of x. And then this e, we're calling it an error variable. Now, in other statistics books, and I even took a class just on regression, they don't use an e here. Because if you notice, we have a Greek letter alpha, a Greek letter beta. So they stick with the Greek letters. And this e, you may actually see that as an epsilon, which is just looks like a backwards 3. For our book, we'll use e, but if you see it somewhere else, that's what that plus epsilon means. It's your error. Oh, sorry. Another name for the deterministic function of x, so this alpha plus beta x, this is also called your population regression line. So alpha plus beta x is your population regression line, where alpha is your y-intercept, there's a huge typo in these notes here that I just caught. So the simple linear regression model assumes that there is a line with a y-intercept of alpha, and it should say slope beta. So that second y-intercept should be a slope. See, it's right in the PowerPoint. So on your notes, it should say slope beta, not y-intercept beta. And it looks like that one that I just showed y'all. Y equals alpha plus beta x plus e, in our case, or epsilon. So without the random deviation E in the equation, all observed XY points would fall exactly on the population regression line. In other words, we wouldn't have a graph like this. These points would all be on the line here, not off of it. But with our error term, we're allowed to have other points not on the line. So let's kind of label what's going on here. Of course, our intercept is alpha. So our intercept here is the alpha. The population regression line, which is the first piece here, has a slope of beta. And then the distance from the regression line to the point itself are the error terms. And notice I use subscripts here. E sub 1 and E2. E sub 2. I could really go into detail as to why we use subscripts, but the main reason is when you do a regression, it's actually all matrix algebra. We're not going to go into matrix algebra, though. We'll leave that for a college level class on just linear regression. Or not linear regression, but regression in general. Okay, so let's turn to the next page and look at some assumptions of the simple linear regression model. And these assumptions all tend to center around the errors. They all tend to center around your errors. The first assumption is that the distribution of E, of your errors, at any particular value of X has a mean of 0. That is, the mean of your errors will be 0. The standard deviation of your errors is the same for any particular value of X. And we denote this with sigma, just like we have for most standard deviations. Now, as far as regression output goes, we tend to say that this is S sub B, which we've seen that before. You may remember that from chapter 5. The sample standard deviation of the errors. The distribution of errors at any particular value of X is normal. And last but not least, the random deviations associated with different observations are independent. The errors cannot depend on each other. And we'll see by the end of the day tomorrow how to determine whether the residuals or the errors are independent. Okay, so let's look at the height and weight of a population of adult women. They're treading kind of dangerously here, looking at the weights of women.
That's a dangerous game.
Yeah, very dangerous. Okay, so let's say an adult female is 5 feet tall, or if you look at the graph, we're dealing with inches here, so 60 inches. How much do you think an adult female should weigh if they're 5 feet? Yeah, smart thing to say is, let's not answer this. Let's see what the graph says. We'll just go with what the book says. That'd be the smartest thing to say. Okay, so they give this range of heights here, or range of weights for the height. The weights of women that are 5 feet tall will vary. So in other words, there's a distribution of weights for adult females who are 5 feet. Now notice, when you come close to this area, they start getting clustered, then they start spreading back out again. That's because at each individual X, remember we said the errors are normally distributed. So, are some weights more likely than others? Sure. At 60 inches, the heights have a normal distribution. Then you move like to 62 inches, that have a normal distribution. 64 inches, normal distribution. So we would keep going in that manner. And if you looked at the mean at each of these, and then connect the dots, you would have your regression line. So if I looked and said, okay, here's 60, the mean is right here. 64, the mean is about right there. 68, the mean's about right there. Connect those 3 dots, you have your regression line.
We give it cube and increase it. We just want to decide this cube is good.
True. Very true.
Oh, it's like big cube.
Yeah. Yeah.
It's not 27.
Yeah. Okay, so we want the standard deviations of all these normal distributions to be the same. So if you notice the curves all look to be about the same, that's because they have the same standard deviation. Okay, so let's again review the basic assumptions. So the distribution of errors at any particular x value has a mean of 0. So remember, the variable e is a measure of the extent that an individual y value deviates from your population line. So on average, it wouldn't deviate much. Second assumption, where they have the same standard deviation, for any particular x value, the standard deviation of y equals the standard deviation of the errors. So that's why they're all the same, because the standard deviation of y doesn't change. And the third one, the normal or the distribution of e at any particular value of x is normal. That's because the distribution of y at any particular value of x is normal. Okay, so let's look at page 3 now. We're going to get into more of the calculations and where we'll actually need our calculator. So we're going to use, we're not going to really worry about the error much when we're calculating. We're going to use y hat equals a plus bx to estimate the true population regression line. Notice here that we're doing an estimate. That's why we have the hat on there. If we left the hat off, this would be a deterministic model. We don't want deterministic models right now. So we're estimating the population regression line. To find B, yes, we can use our calculator, plug the data in, it gives us the regression line, and we're done. But we can also calculate it. We can do the standard deviation of xy together, divided by the standard deviation of your x's. To get A, that's going to be a point estimate of alpha, which is the average y, so y bar minus b times x bar. And then to get each of these, at least for beta, s sub xy, we would use this first formula. And s sub xx, we use the second formula, which looks complicated, except for the fact that your calculator pretty much gives you each piece. You don't have to calculate hardly anything. And if we let just x star denote a specific value of the predictor variable x, in other words, we're just picking an x. Let's say we have this line and we pick a random x. Then when we plug that in the regression line and we say, oh, well, y equals whatever the model tells us. This can be interpreted two ways. The first way is that it's a point estimate of the average y value when you're at that x. So if we look at our graph, I'm not going to go back on the slide, but if we look at our graph on page 2, if we pick the red point at 60, that's the average y when x is 60. We go up to 64, the red point is the average y when x is 64, and so on. That's one interpretation. The other is that it's a point prediction of an individual y value that could be observed when x is equal to x star. So again, kind of using the graph on the bottom of page 2 as an example, we don't have a point on the line that we've already discussed for 62. But if you plug 62 in that equation, then that would be a prediction for the y value, whatever we got there. Like I said, we've done quite a bit of theory up to this point. So if you're just like, yeah, enough with the theory, give me some calculations. We're getting there. That's what we're about to do now, is a big old calculation example. Okay, so medical researchers have noted that adolescent females are more likely to deliver low birth weight babies than are adult females. because low birth weight babies have higher mortality rates, a number of studies have examined the relationship between birth weight and mother's age for babies born to young mothers. The following data is on X being the age of the mother, Y being the birth weight of the baby in grams. Just for the sake of this example, when I was doing my notes over Christmas break, I'm like, that doesn't tell me anything, at least. I mean, here in the U.S., we use pounds. When a baby's born, they weigh this many pounds. So, just for the heck of it, I went and found that there's approximately 454 grams in 1 pound. So if that was you and you wanted to figure out the pounds for each of these, you could. Anyways, what we're going to do with this data is we need to first do a scatter plot. Let's do that. Let's first get a scatter plot. I gave you the axes. All you have to do is plot the points. I'll give you all a second to plot the points. Okay, so that's what your scatter plot should look like, somewhere close to that. Notice that the scatter plot shows a linear pattern, and the spread in the y values appears to be similar across the range of x values. This supports the appropriateness of a simple linear regression model. Good to me. Okay, so next thing we want to do is compute summary statistics. And we can do this in the calculator. So what I want y'all to do is in L1, enter the x values, and L2, you'll enter the y values. So x1, you put L values, L1, you put x values, L2, you put y values. So stat edit. Give me a second to get these entered. And then instead of doing one variable stats like we've been doing all semester, you're going to do two variable stats. So now once we get our numbers entered, we'll do stat, calc, and two variable stats instead. Hopefully you put your x's in L1 and your y's in L2. Do that and calculate. I'll give y'all a second to get caught up. Okay, so you look on your notes, it asks us for n. So based on the one variable stats, what would our n be? 10. What about the sum of the x's? 170. Yep. Sum of the y's? That's right. The sum of the x squareds? Yep. The sum of x times y? That's right. And then the sum of y squared? That's right. And then there's two more you may want to write down since the calculator gives them to you anyways. Maybe you want to write it down below the sum of the y squared. You'll eventually need x bar and y bar. So x bar would be what? 17. And y bar is that's right. So what these values will enable us to do is calculate the predicted regression line, the estimate of the true regression line, using the formulas that we talked about at the top of this page. Okay, so there's our summary statistics. Let's calculate the items they ask us to calculate. So first, they ask us to do S of XY. And let me add what we added. We added X bar, and we said that was 17. Y bar, we said it was 3004.1. Okay, so S of XY, our formula was to do the sum of XY minus the sum of X times the sum of Y divided by N. So our sum of XY was 515,600 minus 170 times 30,041 divided by 10. That means S of XY is what? Once we plug our numbers in, that's right. 4,903. Okay. Then they ask us to calculate S of XX. So we do the sum of the x's squared minus the sum of x squared divided by n. I'm just going to box these in, that way they stand out here in a second. Okay, so the sum of x's squared, 2910 minus 170 squared divided by 10. Yeah. Okay, and then next ask us to calculate B. So that's our slope. You do S of xy divided by S of xx, which means we have to do 4,903 divided by 20. Do 45.15. And then on the back, I'm not going to change slides, but on the back, we have to calculate A and then get the regression line. So I'm going to do all that on this same slide. So let's get A. For A, we have to do y bar minus B times x bar. So we were told that y bar is 3004.1 minus 245.15 times x bar, which is 17. And A will be a fairly large negative number. If you're wondering if you got it right or not. That's right. 1,163.45. There's our A. Then it says the estimated regression line is blank. I'm going to write that up here at the top. And we're going to have our intercept comes first. That's our A. So negative 1,163.45 plus 245.15x. So what we just did was found the regression line by hand. If you weren't sure whether you did it right or not, you could also do linear regression, do it in your calculator like we did in chapter 5, and you'll find that it's the same thing. We just did it by hand instead of letting the calculator work all the magic. Okay. So what does the slope represent in our regression line here? Think back to our exercise that we did when we talked about this. How much the weight increases when what happens? Yeah. So slope is the weight the baby increases for each increase of 1 year in the mother's age. That's what our slope tells us. Okay, so next thing it asks us to do is, what is the point estimate for the mean weighted babies born to 18-year-old mothers? What can I do to answer that question? Plug in 18 for x, that's right. So when you're doing this on the AP test, there's 3 steps that I would do for a problem like this. First one, it's already done for us. Write the equations. Second step, show where you actually plugged it in. You don't have to label them like 1, 2, and 3. I'm just doing that for emphasis. And then once you do that, third step is where you actually do your answer. So y hat equals. That's right, 3,249.25 what? Well, grams. Being that we're talking about the weight of a baby, in case you're curious, that's a little over 7 pounds. Seven, 8, somewhere in there. When you get down to 6, they're getting a little small. Yeah. Yeah. Okay. I need to erase all my writing because it looks like gibberish. Okay, so this is the point estimate for the mean weight of all babies born to 18-year-old mothers. Another way we can interpret this is the prediction of the weight of a single baby born to a mother 18 years of age. There were 2, in case you didn't catch them, there were 2 blanks within these bubbles. All was a blank, and then single was a blank. Okay. The statistic for estimating the variance sigma squared of the model is S sub e squared is sum of squared residuals divided by n minus 2. And even just this may start ringing some sort of bell, like in the back of your head. I've seen this before. I think I've seen it before. Maybe. Don't know for sure. We've seen something similar to it. We've for sure seen sum of squared residuals in chapter 5. It's like it sounds. You take the actual y minus the predicted, square it, and then add them up for all points. Sum of squared residuals. The estimate. Oh, let's back up. Before we get to that point, the subscript of the e reminds us that we're estimating the variance of the errors or the residuals. which in turn is the variance of the model. That's why on the mini-tab output that we talked about in Chapter 5, we talked about the standard deviation. Yes, it's of the model, but it's in particular the standard deviation of your errors. The estimate for the standard deviation, sigma, is SE, is just being the square root of this piece up here. So the way we said it in Chapter 5, we actually wrote it out. Sum of the square root of the sum of squared residuals divided by n minus 2. That's what should really ring the bell. If I scratched, don't do this, but if I scratch that part out, this should ring the bell. Note that the degrees of freedom associated with estimating sigma squared or sigma in the simple linear regression is n minus 2. So we have n minus 2 degrees of freedom. Anyone want to take a guess at why n minus 2 degrees of freedom? You can even look at the notes at the bottom and it kind of gives you a hint. Not quite. We're not estimating as are observed. We're estimating alpha and beta. Those estimates are our A and our B. Since we have two estimates, we have to reduce the sample size n by 2. If we had more things that we were estimating, we would have to reduce it by even more than that. And then recall that the coefficient of determination, which is r squared, is the proportion of observed y variation that's attributed to the model relationship. And you may remember that r squared is equal to 1 minus the sum of squared residuals divided by the total sum of squares. Okay, so let's revisit that birth weight example that we have been dealing with. They ask us to find the sum of squared residuals and total sum of squares. We did this in detail in Chapter 5. I'm going to give those to y'all and then just make a note here to see Chapter 5. For an example of how to calculate. I mean, I gave you all the formula there, but if you want to see like an actual worked out example, we did a full-blown one in Chapter 5. And they're asking us to use these to calculate the standard deviation and the R squared. So let's do standard deviation first. So we need to do the square root of what? What number do I put on top? Yes. SS residual goes on top. And what do I divide by? And minus 2. What was our n in this case? 10. That's right. I'm going to do 2 decimal places, so 205.31. So that's our standard deviation. Now we want to do R squared. This will be 1 minus sum of squared residuals over total sum of squares. And again, let's do this one to 2 decimal places. It is. Okay, so now let's talk about what each of these mean. First, standard deviation. That means for a particular mother's age, the typical deviation for possible weight to babies is approximately 205 grams, which is roughly about half a pound. That's a typical deviation. And then for the R squared, that means approximately 78% of the variability. I need to add the word in here. In observed with the babies can be explained by this model. So approximately 78% of the variability in the observed weight of babies can be explained by the model. Okay, questions on this example? That's it.